indeed, today I wanted to talk a little bit about leveraging system architecture models for diagnosis of high-tech systems. This is, the work we did this is a presentation about the work we did in the past couple of years together with one of our industrial partners. Basically, I'm also looking a lot for input from your side. You're the experts here. I'm not really an expert on Capella itself, but I'm always interested in getting your feedback as well on what we are trying to do. So first of all, who am I? I'm a researcher in TNO-ESI to be more specific. So TNO is a the Dutch Organization for Applied Scientific Research in the Netherlands, and in TNO, there's a department called Embedded Systems Innovation, ESI, and there they are focusing very much on the high-tech sector in the Netherlands. And then inside ESI, there's a smaller group which is focusing very much on intelligent diagnostics for those high-tech equipment manufacturers. So ESI at a glance, what is ESI? It's a group of people, about 70 people we have now. Part of them, about 10%, also works part-time at the university as a professor. What we're trying to do is to bridge from academia to industry to develop methodologies to help our Dutch ecosystem of high-tech companies to stay competitive. So we have a couple of partners you see on the right-hand side that we often work together with. Part of the partners is also is a university. So we have 5 universities as a partner right now, and on top of that we have some implementation partners who can help us in actually maturing the methodologies that we develop and really embed them in the high-tech industry. So the outline for today, I will first start with model-based systems engineering for model-based diagnostics. And for that, I will start with telling you a little bit about model-based diagnostics, what we're trying to do, because I think you should understand what our target is first. Then I will introduce our methodology, show you a demo. Let's hope the demo effect doesn't kick in. And of course, we will round up with some conclusions and future work, which is also some sort of request for feedback from you guys. So let's start with the model-based system engineering for model-based diagnostics. So model-based diagnostics is not a new field. It has been around since the 1980s already. Originally stems from the medical domain. And the main idea is, of course, to use formal models to compute diagnosis based on what you observe from either a patient or a system or anything like that. So that is essentially what it tries to do. There are several formalisms available for doing this kind of reasoning. So you could use some sort of logic formalism, you could use probabilistic models, you can use neural networks, any kind of formalism that is able to do this kind of inference or reasoning would do. Of course, there are pros and cons for going for one of them, but our approaches mainly lie in the field of probabilistic graphical models, such as Bayesian networks or Markov networks. So I will give you a quick, short introduction into, let's say, Bayesian networks. Just bear with me, it is a very short introduction. So a Bayesian network represents a set of variables and their conditional dependencies. So basically, you express a number of variables like this. We have 4 variables: cloudy, sprinkler, rain, wet grass. Each of them can have can be in a certain discrete state. Like it can be cloudy and it cannot be cloudy. It can rain or it cannot rain. And basically, by putting edges between those, you express some sort of conditional dependency from one on the other. So rain is, for example, depending on whether it is cloudy or not. We express those dependencies by conditional probability tables. And for example, for the variable cloudy, it can be yes or no. And in this case, it doesn't depend on anything. So that's what we call a prior probability distribution, where we have a 60% chance of having clouds, being cloudy, and a 40% chance of not being cloudy. Then, of course, for the rain, it depends on cloudy. So if it is cloudy, there's a 70% chance of having rain and a 30% chance of not having rain. If it's not cloudy, there's a 10 to 90% chance. Of course, you can do that for all those variables, and together they make one Bayesian network. And well, okay, now you may ask, what are you going to do with this kind of information? But basically what we can do is we can, well, instantiate such a Bayesian network, insert evidence of what we know, for example, and then compute the posterior probabilities of the other variables we have in a network. So this evidence can either come from a system, from an observation, or a measurement, or anything like that. Can also be an assumption if we don't know for sure, but we just want to do a sort of a what-if scenario. Basically, what we can do is we can say, okay, let's assume that it is cloudy. That gives us, let's say, some sort of probabilities here, but also a probability of the grass being wet of 68%, 68% and 32% being dry. Of course, for diagnosis, this is actually the opposite. We probably would observe that the grass is wet, and we would like to know what the probability is that it was actually cloudy, or that it was maybe caused by the rain. So based on, again, the prior probability of cloudy and the conditional probability tables of those of the sprinkler and the rain, we could say, okay, if we don't have wet grass, the grass is actually dry, then apparently there is a almost 50-50% chance of being cloudy. And this is exactly how we are also using diagnosis for high-tech, use these networks for diagnosis in high-tech systems, because essentially based on some observations, you could actually compute what the most likely problematic parts in your system are. Of course, that is not easy. So if we want to do this for high-tech equipment, then we talk not about 4 variables, we talk about thousands of components and also thousands of observables that can be made. So it is an incredible challenge to create a diagnostic network that is this big. So how to scale this? Where and how do we get the required information that we need to put in our model? So that's a massive challenge, which is also what we are aiming for solving at least. So there are several ways of constructing such a probabilistic model. One of them is by learning it from data. So you can, of course, collect a lot of information from your systems in the field and then have some sort of model learning algorithm applied on it and learn some model. However, that requires a huge amount of data, and that amount of data is not always available. I mean, sometimes you just design a new product and you then bring it to the field, you start selling it, and well, that means you simply do not have the data to start with for learning some sort of model. So if there is insufficient data available, then you would rely on experts to make those models. However, there are very few experts on probabilistic modeling, and often people don't really feel at home in creating those kind of models, especially because it's quite difficult and error-prone to start defining those probability, those conditional probabilities in a big model. So why not try to leverage already available structured information? Of course, you know where I'm going for. So the high-tech industry that we work with is gradually adopting model-based approaches for several reasons. I mean, you could talk about requirement management, having some sort of unified language, which was also expressed in the previous presentation. You could think about code generation, configuration management, some sort of virtual prototyping of yours, either some aspects or the full system. But there are many reasons for going for model-based methods in the high-tech industry. Capella is one of the tools that is being used for this transition, but of course it's not the only one. There are plenty more that are being used, but in this case, and for today, I will be focusing on Capella only. And what we see is that the main ingredients that we need for doing diagnostics for high-tech systems are actually present in the Capella model. So if we start reasoning, well, diagnostic reasoning for a system, then you start usually by saying, there's some sort of functionality that I expect from my system that's simply not working. What could be the cause? And then you start thinking about, okay, but what does that functionality depend on? This is also the kind of troubleshooting that is being done in the field when service engineers are trying to troubleshoot your system. So this kind of information is actually available in Capella. You have functional decompositions, you have hardware decompositions, you have functional dependencies of one to the other. And then you, on top of that, you also know which hardware, to some level of detail, of course, is responsible for which system functions to be executed by our system. So why don't we just try to tap into this body of knowledge to create the diagnostic models that we need? So this is just a brief introduction to the methodology that we have developed. So I will now give you a small picture of our methodology that we've developed. It is still a prototype, right? This is not a full-blown product that can be deployed anywhere. It is a methodology that has been developed based on, of course, the information available in the partner companies, our prior knowledge about, well, how to do model-based diagnostics, etc. So we start with system descriptions on the left-hand side. These system descriptions can be anything, can be structured, can be non-structured. Could also be Word documents, PowerPoint presentations, but let's say people have, well, companies have a system design and they document that in some way. What we try to do is to use some sort of interface to interact with the user to create this diagnostic model, to formalize that kind of design information in some way. And from there, we create a diagnostic network. And this diagnostic network represents all the information that we need to capture for, of course, doing diagnostics. Capella is one of the structured sources of information that we try to use here. So there is a semi-automatic transformation to go from a Capella model to a diagnostic network. And I will show you an example of that later in the demo. I'm saying semi-automatic because not all information that we need in our diagnostic network is present in Capella. From this diagnostic network, we could generate some sort of reasoning model that we can then use to do the diagnostic reasoning. This reasoning model has what could be, for example, a Bayesian network. That reasoning model can be used by an analyzer, which then generates some diagnostic insights in, well, what failures can be observed, what failures cannot be observed, which is some sort of feedback to the engineering team designing the system to think about whether or not they should add more observability to the system, which could be placing additional sensors. It could also be about creating additional tests for your system to self-diagnose, for example. Also, this reasoning model is used by a diagnoser, and the diagnoser essentially gets input from the system in the field, which spits out a lot of operational data, and the diagnoser can then compute the diagnosis, assuming that there's a problem, of course, and generate a list of diagnostic steps that can be taken, which are presented to a service engineer. The service engineer executes them on the system itself, acquires new data, feeds it back to the diagnoser, and there you go. There you have your what we call the operational diagnostic loop, which is essentially the troubleshooting the service engineer does. All of this middle part, with all the green edges, is implemented in some Python library that we call mbdlib. It's not open source, at least not yet. Which is the model-based diagnostics library that we have developed to be able to experiment with our proposed methodology. So this diagnostic network, what does it really contain? So it contains several types of nodes. For example, we talk about hardware, we talk about functions, we talk about operating modes, And then there are some observables like direct observables and diagnostic tests. And well, a diagnostic test will yield some test results that again give you information about, for example, the hardware or the function. So those are essentially the building blocks of our network. And then there are several types of relations that connect those different types of nodes, of course. So, for example, the realizes relation expresses that some hardware component realizes a certain function, a system function. Then, for example, the required for relation is, well, connects one function to another function, where the first function is actually providing something to the second function. So that is all captured in our ontology. And if you look at this, well, of course, there are several types of nodes and relations representing all sorts of different things in our, well, in the eventually realized systems. But luckily, half of it is actually available in Capella model, at least following our methodology and our interpretation of the Capella models. So that's very good. So now let's have a quick look at a very simple Capella model that we have. So this is a CD radio player, relatively high level in this case, but we have essentially 4 logical components: a power system, a CD reader, a radio receiver, and an audio system. So this is, let's say, also the 1990s type of CD radio player that you could have, where you could select, or you have a switch to actually select the CD player or the radio signal, or maybe even the cassette player, but that's not included here. That's essentially the system that we have tested it with. Of course, we also conducted case studies with a partner company that we conducted this research with. However, those are confidential and I cannot present them. Also, that is unfortunate, of course, but I'm trying to illustrate it based on this example. So this is the model we have, 2 functional chains. And now let's try to create a diagnostic network based on this kind of information. So first of all, we look at the power system, for example. Because it's a logical component, we know, okay, let's assume that logical component will eventually be some hardware, some piece of hardware realizing some function. Well, the function is, of course, also deployed here. So to provide power, we should also add that. Power system realizes provide power. Okay. Purple, by the way, is a function. And yes, I know, unfortunately, this color scheme doesn't correspond to the Capella color scheme. Maybe we should change that. So now, again, for the CD reader, which realizes the read CD function, and of course, well, then there's another edge going, well, there's provide power, which is apparently providing something to the read CD, where we assume that the read CD requires that one in order to function itself. So that's where we add a required for relation from provide power to the read CD. Of course, we also add the radio receiver. The radio receiver realizes the receive radio function. And of course, this is all very high level, right? So again, a required for connection. For the audio system, we do the same. Then we have those 3 edges coming into the audio system's main function, the generate audio function. So we add them as well. And then there is something we consider to be an operating mode, but this is also where I'm very much looking forward to your feedback or criticism on this kind of approach. Because in this case, we have chosen to create 2 operating modes, one for being able to play the CD and one for playing the radio, but those are mutually exclusive in our system. So that's why we implement them or interpret those operating modes at, well, those functional chains, sorry, as operating modes. So basically what this operating mode does, it lets this generate audio select one of the 2 audio sources that it can select from, basically giving you again information about how you should be troubleshooting your system, right? Because if you're listening to a CD, for some reason that doesn't work, then there's no point in troubleshooting the receive radio. Very much simplified, but okay, that's basically what we try to represent here. But again, this is an assumption that we made. So now we have our initial model based on the Capella transformation. However, there is still something missing, so we still need to add some sort of observability to our model. So logged events or diagnostics tests that can be executed on our system should still be added to this simple system. Unfortunately, that information is not available in the Capella model, so we have to add that manually after importing this sort of model. So let's say that the read CD function can report some sort of error on the little display we have, which is then the CD error. The receive radio also can report a problem on the display. And let's say that we can test by just, can we hear audio? We have a listen audio test that results in a variable that tells us whether or not we can hear the audio, which gives us information about the function generate audio. And that's basically a diagnostic test that we can execute. So that sort of concludes our model. Of course, this is not all, because I've now shown you only the logical layer. The thing is, of course, we went down to the physical layer as well, where we have a little bit more granularity in the number of components we have and the way the logical layer is being realized. So this is essentially the final model, and I know you can't read it, but this is just to give a bit of an impression on, okay, it is bigger than just what I just showed you. This is actually the physical layer, a visualization of the physical layer that we have. Actually, we have two different, again, mutually exclusive operating modes. Also on the power system, we can select wall power or we can select battery power. And for the audio source, we can select either one of the two sources. Now, the idea is to go for a brief demo to show you what it looks like to import this model. Then I will make some modifications to it to just illustrate what we do with diagnostics for these kind of models. So this is our prototype tool. So great, we can import a Capella model here. So we just need to select those 3 Capella files. We upload it. We select that we want to import the physical layer in this case, and we automatically, because I just mentioned tests and observables are simply missing, we do generate some default tests at several layers in the hierarchy by default if we want to. We also choose to import those operating modes because I know that in this case those are mutually exclusive functional chains and can be seen as operating modes. So we can just import this. What it now does, it reads the Capella model and it creates this graph database kind of thing out of it, the knowledge graph, and it will store it in a graph database. And this is again a visualization of what we have. We have those 4 subsystems with their main functions, all being a sub-function of the main function to play CD or radio. A test is automatically generated. And that's about it. And of course, it is a hierarchical model. So we have the audio system, we have several different modules again. And the CD reader, we have it as well, etc., etc. So all I need to do now is I need to add some direct observables, like what is it? Well, the CD error and the radio error I mentioned before, because those are not automatically added now. Only tests are generated automatically. So now I have an error, and I need to add the radio error, sorry. Now, of course, you see that those are not connected to anything yet, so I will need to connect them. The CD error gives us information about the system function to read the CD. And the radio error gives us some information about whether or not the receive radio function is capable of being fulfilled. So now you see that we have connected those. So the receive radio is observed by the radio error and the read CD is observed by the CD error. Now, just to make things slightly more interesting, because it now created low-level tests at the lowest level on every hardware component we have, it would be good to also remove a couple of them, because now the system is fully diagnosable at all times. So I know that if we look at the Capella model, you could see that the detector and the transducer are behind each other. So those can both be tested right now. But if we remove both of those tests, then I would expect that it would not be possible to distinguish those from each other if there's some sort of problem later on. So what we could do is just remove some of the tests. So for the for example, the detector, we just remove the test there. And also for the transducer, we will remove the test. And that gives us our final model, basically. So I'm just going up again to the top level. And now, in the beginning, I mentioned we could do two things, right? We could assess the diagnosability of our system as it is designed right now, or we could run operational diagnostics, which is basically the troubleshooting a service engineer has to do in the field. So first things first, let's do the what we call design for diagnostics, the diagnosability assessment. For that, we have to select the operating mode. So let's consider that when we are playing CD on wall power, which is most often the case, then it will compute for us on all the observables we have, which is in this case just one of them, because the radio is now excluded, because we told it that we are playing the CD. It will compute what the observability on, whether or not that error will be okay, which means not being reported, or not okay, which means being reported. It will compute a signature for every hardware part failing, and it will also generate a sort of a diagnostic procedure, which is a sequence of the tests you could do in order to distinguish the failures which have exactly the same signature. So in this case, you see that there are a lot of failures which basically end up in this CD error being reported. Those are all not okay. That's quite a lot of them. And well, in order to distinguish from each other, you should first know, okay, well, do we have power? Yes or no? If that is not okay, then we start digging into the power supply part. If it is okay, then we start digging into the CD reader part, which I think makes sense. What you also see is that after testing the motor, well, if the motor is not okay, then you end up with the motor. But if the motor is okay, it detects that we don't know whether it's actually the detector or the transducer that is being broken, because I just deleted those tests, right? If either one of the two would be testable, then we would have just gotten another blue node here with a split, and then it would be fully diagnosable. So this is just a way, and of course this model is very simple, but this is a way of assessing the diagnosability of your system during the design based on the rather high-level system information that we have available. What we can also do is run the diagnoser. Also there, when we run the diagnoser, it will transform the diagnostic network, the knowledge that we have. It will transform it to the reasoning model, and well, then the reasoning model can be computed or can be used to compute those posteriors, and the result is what you see here. So on the left-hand side, you see the diagnosis. So this is just the top 10 components which are in your system, the hardware components in your system, which are most likely to be broken. In this case, the priors of all the hardware parts are the same. So they are all 1% likely to be broken by default and 99% likely to be healthy. because we didn't inject any problem in the system yet, everything is still at its prior probability, so 1%. On the right-hand side, you see the diagnostic tests where we sort the tests based on the balance of the cost of doing the test with the expected information gain of conducting the test, which is expressed by the conditional entropy, which is again something that comes from the probabilistic network. Yeah, so that is just sorted. And in this case, what we need to do is, okay, we know that we were playing the CD, and we know that we have a CD error. This is just a hypothetical example. So now let's compute what the most probable causes are. Now, again, you see that the power board is suspected, but most of the suspected components are obviously in the CD reader, or in the CD reader composite, right? So the first test that is being suggested is to test whether the power system is able to provide power. In our hypothetical example, as in my expectation is that the motor is broken in this case. So all the evidence that I will now insert will be based on that assumption. If the motor is broken, the power system should still be able to provide power. So there's no problem there. I should turn auto compute on. Well, then, okay, that's eliminated. So does the system generate some sort of audio? Well, no, it does not. Or wait, yeah, no, it does not. Okay, great. Now we should dig into the CD reader, the board of the CD reader. Okay, that's okay, no problem. Shall we test the laser? Okay, that's also no problem. Now we test the motor. Well, okay, it's only one of the 3 components that's left, right? But okay, finally we have it. Great, done. Diagnosis is finished. This is a clear outcome, I would say. Of course, this is a very, very simple system, and because of that, all the suggested tests that are given here are kind of obvious, right? But you can imagine that for a very big system, this is far from trivial, especially if all the tests have very different costs and tests give you information about many, many components all at once, then deciding on what test to do next is a very big challenge. So of course, for this particular example, it is just for illustration purposes, like this is how it more or less works. This is how we can use the Capella model for doing so. But I hope it gives you a bit of an impression. That concluded the demo, at least. So now moving on to conclusions and future work. As I mentioned, we have conducted a couple of case studies with the partners that we've conducted this research with. In those cases, we created one model of the system or part of the system, and that single model could, for all 3 cases, find a satisfactory root cause. It could come down to the root cause of the real problem, right? By injecting real data, interpreted data, of course, but that was a very positive outcome. Also, the reactions that we've gotten so far are rather, quite positive. The methodology, or the diagnoser really mimics the way a service engineer would also do the diagnosis, which is very beneficial because in this case, no real expert knowledge, apart from, of course, creation of the model, is used. So you could actually have a junior service engineer to use this tool as sort of a guide to help him doing this diagnosis. And of course, it's not a tool yet. It is just a methodology. Of course, this is all provided that you could create a model that is big enough. And there are some concerns about the scalability of this. How is it going to work? How is it going to be, how is it going to be working efficiently in a big organization for a very big complex system? And that is still something that, of course, this way of model-to-model transformation may be one solution or solution direction. But apart from that, it is of course also subject to further research to how to do that efficiently. Altogether, the shown approach is promising, both for operational diagnostics as well as design for diagnostics. And what we see is that MBSE models like the Capella one provide a lot of information that we could use for diagnostic purposes. However, there's also still something missing. So one of our big questions is where and how to combine this observability information. It is definitely needed for diagnostics purposes, but it's not really a fit in the Capella model itself. So yeah, if you have any suggestions or experiences that are somewhat related, we are very happy to to learn about them. Also, of course, this toy example model is just one model, and we have now seen also several other models with the companies that we work with, but that is still a very small subset of the companies that use Capella, and is also very much subjective to how Capella is being used in the company. So to what extent all the assumptions that we make to do this automatic transformation still hold for, let's say any model, that is still very much of a question for us. So we also need to build up some sort of experience with with MBSE models in the wild, to say, to actually be confident that this way of transforming and generating those models is a good way of working. And with that, I would like to thank you for your attention. If you want to reach out, this is my email. Very much looking forward to any responses.
Thank you, Thomas, for an excellent presentation. So we have a number of questions in the Q&A channel. So let's go for the first question. Is your approach close to predictive maintenance, health monitoring of technological systems, surveying parameters and deciding to start preventive maintenance when reaching thresholds? And if the answer is yes, then there's another part of the question.
Yeah, it's a very good question. Predictive maintenance is something that is on top of the wish list for a lot of companies, also that we work with. The thing is, most of the predictive maintenance strategies so far focus very much on low-level components like bearings and maybe smaller components, let's say, while Capella very much focuses on a system view. And that is exactly the angle that we are trying to approach diagnostics as well. So we are also trying to tackle system-level diagnostics, and because of that, in extension of that, we would like to go for system-level predictive maintenance as well. So Capella could be a very good way of expressing system-level concepts and connecting it to predictive maintenance, but so far we haven't made any concrete steps in that direction yet, at least not in connection to MBSE models.
Okay, thank you, Thomas, for your answer. Then let's move to the next question. Do you account for uncertainty in the probabilities within the network? For example, when you say 60% change, is it 60%? Is there a way to account for an uncertainty regarding this percentage?
Yeah. You're right. And yes, we do account for it, at least in all the observations that we inject. Let's say the nodes for the direct observables and the test results, which should eventually contain the actual observations we make from the system. There's a way of setting false positive and false negative rates on those. So you could indeed change your certainty about the observations you make. And yes, that will impact the diagnosis.
Okay, thank you. So next question, is the reasoning for diagnosis based on Reiter and De Kleer initial works?
Yes.
Okay, so that's a specialist question and a specialist answer. Okay, thank you. Then moving to the next question, there are a lot of works related with relating MBSE with MBSA.
Yes, we know that there is some work in safety analysis, but we haven't yet found a good connection to the methodology that we try to develop.
Okay.
Yes, well, also safety analysis is, of course, related to interaction in the field, right? So in that sense, yes, there are touching points, touching areas, but so far we haven't considered any of that. If we look at also risk management field, then we see that also on top of SysML there are some extensions for that. And yeah, it is in the planning of exploring those as well and how we could use that.
Okay, thank you. Does the tool provide metrics such as probability of detection, probability of isolation?
Not at this moment, no. But also the tool that we have is still very much of a prototype tool. It is mostly just a vehicle for us to experiment at some sort of scale bigger than just 10, 20 nodes.
Okay, thank you. I was wondering two things. The first one is a detail regarding the way you managed modes. You had to manually add the execution modes on the network side. Did you consider using modes and states from Capella to capture the two modes of your simple example, or in more complex examples as well?
No, honestly, we haven't. As said in the beginning, I am no expert on Capella per se. So we are trying to use the information that we have seen present in the models that we have seen so far. And that kind of information, as far as I know, was not set. And yeah, if it is not being used by the companies that we work with, then of course it is a very good way of still having some sort of guideline for making better use of their models by also using that. But so far the focus has been mostly on using what was present.
Okay, and then you were wondering how to capture the network information, and you stated that it probably did not belong in the Capella model. I was wondering what made you say that? Is it because it's not the same experts who have the knowledge to enter the actual information than the Capella user?
Which actual information are you now referring to?
Yeah. By the end of your presentation, you stated that you were wondering about getting the relevant information about all the probabilities and all the measurement points and all these, if I understood correctly. And you said it did not belong in the Capella model, which just I was wondering why.
Yeah, that's actually, let's say, my interpretation of what I've seen so far. If we talk about observability information, then it is, for example, about KPIs being recorded on the system. Could be about a sensor measurement that is being reported out. If we talk about tests, it could be some sort of automatic procedure that the system uses to align itself, or some sort of module. And what we have seen so far is that the people designing those kind of tests and knowing how to exactly interpret the results are not necessarily the same people who are architecting the system. And I also haven't found any concepts in Capella, modeling concepts, that would allow, in a natural way, to actually extend in that direction to add it automatically to the model.
Oh, yeah, you're definitely you're probably right. There is nothing out of the box for that in Capella, but I believe the extensibility mechanisms of Capella would make it easy and possible to enrich the data model to support this kind of thing. So I was wondering if you considered developing a dedicated viewpoint to capture this information and have, better information to make your transformation to your network more robust, because it seems to be one of your challenges.
Yeah, no, one thing we have thought of, but will not pursue right now because we're not trying to develop a tool per se, is indeed to have some sort of extension on Capella, where that extension is aware of what concepts, what functions we have in the Capella model, where you could simply add indeed observables, direct or tested, whatever, add them to your model and immediately connect them to the appropriate functions or hardware parts that are being observed. That would be ideal, because then indeed we have all information in one place. But yeah, that basically requires indeed implementation.
Absolutely, and then implementing the practices with the associated actors. So a number of challenges ahead of you, but that's quite interesting. We'll move on to the next presentation. Thank you very much, Thomas.